All right, now we're starting chapter 5. Chapter 5 starts out talking about areas and distances. Okay? What we're going to do is we're going to relate antiderivatives to areas. Okay? That will come in the next few sections. The first thing we need to learn is something called Riemann sums, named after famous mathematician Bernard Riemann. Okay, he's the one that showed the link between these areas and the antiderivative. Okay, and we're gonna learn what that relationship is. Okay, so what we're gonna do is we're gonna look at the graph y is equal to x squared from x is equal to 0 to x is equal to 1. There's 1. Let's see. That'd be 1 right there. It would start here. And then the graph would look something like that. Now, what I'd want to do, I can make it solid. What if I wanted to know what the area of that shape is? It's a very irregular area, okay? If it was in the shape of a triangle, like if this was y equals x, you don't have to write this down or anything. If it was y equals x from 0 to 1, it would just look like a triangle like that. We would be able to find the area of the triangle. Now, very weird shape, okay? How would we find the area? This is done by Riemann sums, okay? What Riemann thought of is we can approximate this area by drawing rectangles, okay? If we find the area of these rectangles, we add up all the areas, and it'll give us an approximate area for this shape. So let me go ahead and redraw the picture, and let me show you what I'm talking about. I missed a little bit. Let's just scoot it over. There we go. Okay, now let's do a very, very basic case. And let's say our rectangle, when I say rectangle, it could be a square. Okay, a square is a rectangle. Okay, so for our first approximation, we're going to say that the area of this shape right here, remember the area, it's called the area underneath the curve and above the x-axis, is about this rectangle, or this square here. Well, the square's length is 1, the square's width is 1, so we could say the area is approximately 1 times 1 is 1, okay? Now, as you can see, yeah, I'm getting this area down here, but I'm also counting this entire area right here. So, this area is an overshoot. I overestimated my area. Alright, well, let's see if I can do better. You always want to see if you can do better. We can do better. Go ahead and do that. Just write over these. Now let's go ahead and split this up into 4 different rectangles, okay? We did 1 rectangle. Let's see what happens if we split it up into 4. Now what I'm going to do here is I'm going to make them all equally sized rectangles. That means the width of them are all the same. So if this is a line segment going from 0 to 1, if I were to split it up in 4 equal parts, that'd be 1/4 here, 1/2 here, 1 3/4 here, and up to 1. So each distance is 1/2, 1/2, or sorry, not 1/2, 1/4, 1/4, 1/4, 1/4. Okay? So this little distance right here, we call delta x. And in this case, our delta x is 1/4. Now what we do is we're going to draw rectangles. Now, this depends on whether you want to do a left approximation, right approximation, or a midpoint approximation. I will show you the details of each one in the examples that we are going to do. Okay? Let's just say in this case this would be a right approximation. I'm going to take this rectangle. I'm going to take this rectangle, and that rectangle. I'm going to find the areas of these rectangles. I'm going to add them up, and that's going to give me an approximate area for my area underneath the curve. Now, if you recall, if I were to draw my other big rectangle, the really big rectangle, if you recall, I had a lot of area, extra area that I was counting for. Now here, you do see extra area right in here, right in here, right in here, and there is going to be some over here, just like really smallly drawn, you can't really see it. But you could see that this extra area is not as much as the extra area when we use one rectangle, okay? So if we used 4 rectangles, we got a better approximation. It's still an overshoot, as you see I'm accounting for more area. We could undershoot, okay? We'll see that in the examples. But now, I would say go ahead and look at my, my notes to get a better picture of what we are doing here. Way better drawn. I pulled this image from the book. Let's see. The first graph, it says n is equal to 10, and it gives you the area. They say R10, like this, R10. We use the number of rectangles. We use 10 rectangles. So that means we split the number line 0 to 1 into 10 equal pieces and made rectangles like that. So our delta x there was 0.1. I'll show you how to get your delta x. There is a formula. And then the next image, if you notice, n is equal to 30, you see that those rectangles better fit the area under the curve. If you go up to 50 and even higher, let's see, yeah, if you go up to 50 and even higher, the area gets better and better. Let's see, oh, I know what the two different images are. The top one is using a right approximation. Never mind, R is not the number of rectangles. R is the right approximation. Right approximation with 10 rectangles. L is the left approximation with 10 rectangles. So if you compare the two, if you notice the areas, if you go up to n is equal to 50, is 0.3434, and the left is 0.3234. So you know the true area must be between those two values. Now, if you were to use more rectangles, you're going to get a better approximation for the area. So this is what Riemann noticed. So let's see, it says the area of a region S that lies under the graph of a continuous function f between the x values x equals a to x equals b is the limit of the sum of the areas of approximating rectangles. Okay, let's go ahead and illustrate what that means. If I have some curve, whatever it may be, this is x equals a, this is x equals b, This is my function f. It is continuous, right? And it is saying that this area underneath this curve between these x values and above the x-axis, so this right here is A, the area is equal to the limit as n goes to infinity of f of x1 delta x plus f of x2 delta x plus dot 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 plus f of xn delta x where delta x is equal to b minus a divided by n. Here, n is just the number of rectangles that we have, okay? So this gives us a way of computing the area, okay? If we specify what n is, n going to infinity, we can't do an infinite number of rectangles. I mean, you can. There are ways of doing it, actually calculating limits and whatnot. But what this says is, you take your first point, you plug it into the function, you multiply it by the distance, the dx, the same distance, because if we were to think about a rectangle here, how are we going to get this f of x and delta x? What are those values? So if I were to break this up into rectangles, and let me use a different color. Let's use black for my rectangle. So remember, the spacing here is delta x. Now, think about the dimensions of this rectangle. Okay, let me draw this rectangle over here. The width of this rectangle is delta x. Okay? That's why every one of these terms has a delta x, because every rectangle I draw has the same width. That's delta x. Rectangle there. Rectangle there. That's delta x. So the width of every rectangle is the same. That's why it appears everywhere in each term. But now let's look at the height. Now, this point right here goes all the way up, and that's the height of the rectangle. The height of the rectangle is its function value at whatever point that is. We could say that this is x1 right here, then x2 would be this next point right there. x3 would be the next point right there, so x1, x2, and those all correspond to the function values at that x value. So the heights here, f of x1, that's the height of the rectangle, that's the width of the rectangle. How do you find the area of a rectangle? Area of a rectangle is length times width. If I take the length, multiply it by the width, that's what we have here. So this is the area of one rectangle, plus the area of the next rectangle, plus so on, plus the area of the last rectangle. To get the entire area, all you do is you just keep adding up all the rectangles, and you have an infinite number of rectangles, okay? Now, the spacing between rectangles is very easy to compute. You take the upper limit minus the lower limit and divide it by how many rectangles you have, okay? Now, we're going to do this for examples. We're going to concretely specify our function, concretely specify our upper and lower bound, concretely specify our number of rectangles, and go ahead and approximate what the area is for the function we specify.